Hello. Good morning, all of you. So, as we discussed last lecture, we are in the unit number 7, and we're discussing about the peripheral features of the peak controller. So, in that, we are discussed starting with the timer 0, timer 1, and timer 2. And after that, the most important function of these, that is the CCP module. Okay, the two CCP modules are there in the peak controller. That is the capture, compare, and the PWM generation. And after that, we discuss about the watchdog timer, how it will be monitor continuously the operation of the processor or the CPU unit. Okay, and whenever the software failure occurs, it resets that peak controller automatically by using the watchdog timer T out occurs. Okay, the next last on chip peripheral we have in that peak controller, that is called as the ADC. And the similar part we discuss interfacing of ADC with the 8051. Why? Because in the as we discussed, 8051 don't have the on-chip that ADC device, additional device. But in case of peak, we have this all the what we discussed, the on-chip devices internally inside the IC. Okay, so the need is what we have to convert analog to the digital conversion, because we know that the control always understand only a digital language, that is the binary format. Okay, and whenever we are interfacing some analog sensors or inputs to the controller, okay, that will be converted into the digital format, and that digital data will be understood by the peak controller, and based on that we need to take the action. Very simple example is that we need to interface LM35 to the peak controller, one of the. So in this peak controller we have the 10-bit ADC. So we can say that the MCQ is asking like this: what is the size of ADC and how many number of inputs are there in case of peak controller? Okay, so 10-bit ADC is available in case of the peak microcontroller, and the number of input channels. So 5 will be there when we have the 28-pin peak microcontroller, and 8 input channels are there for the 40 or the 44-pin input channels. Okay, so what is the meaning of this 10-bit, 8-bit ADC, and how that will respond to the resolution of input signal? That we'll see first, and then we'll go with the exactly block diagram of ADC. Okay, so I'll take the next slide so I understand that. Okay, so 10-bit ADC, the meaning is that the resolution of ADC, the formula always given. So what is the minimum voltage can be measured, that depends upon the resolution and the size of ADC. Okay, so R is equal to the V reference voltage. What is the apply voltage you're applying? Divided by 2 raised to n minus 1. That is the formula to find the resolution. And that will give the 5 volt is the supply voltage I'm assuming. So it operates from the 3.2 to the 5 volt. Okay, divided by 2 raised to n. That is 2 raised to 10, nothing but 1024 minus 1. 24 minus 1. So that gives 5 divided by 1023. And when we do this division, this will approximately is equal to 4.88 millivolt. Means whenever there is a change in analog input voltage from it's nearly equal to 5 millivolt, I can say it's 5 millivolt. So whenever there is an input change of 5 millivolt occur, the corresponding ADC output will be changing there. That is meaning of the resolution. Okay, and this analog input signal, I am applying one of the input channels are available. So 5 input channels are available when the 28 pin will be there, and 8 input channels are available when the 40 pin IC is there of the peak 16F877A IC or 44 IC pin. So I can apply any analog signal which varies simply 0 to 5 volt DC signal. I can apply to the one of the input channel either it is 5 pin, 8 pin. Okay, and correspondingly, how this ADC converts the that input in coming signal from 0 to 5 volt into appropriate 10-bit data. Okay, so previously also we have seen that how it converts. So D0, so I can say it is a D number 10 bit. Then we have D9. Like this, we have the 10 bits. So I can say this will be D1, last will be D1. And here is my input analog voltage. Okay, so this is my input analog voltage applied P in. So whenever the input will be 0, by default I am getting the 0, 10 bits like this. Dot, 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 0. So it's starting with resolution of 5 millivolt means what? Next value will be 5 millivolt. It's multiple of 5 millivolt. So 5 millivolt correspond to provide the first 10 bit output, that is the 9 times 0, 1. So how it converts, I have shown here. The first will be like this. So I can set D2 here, no issue. Then 10 millivolt we have. Then 15 millivolt. It goes multiple of 5 only. Yeah? So like this 20 millivolt. Last dot dot dot, it will be 5000 millivolt. Correspond to 5 volt. So when the supply voltage will to maximum 5 volt input signal, that time all bits will be 111. Like this, it provides the digital 10-bit data. And this digital 10-bit data inside that control register ADCR, we have the data register for the ADC. That data will be saved, and I can read the what is input signal applied corresponding digital data. So like this ADC, in the size will be 10 bit, it provides the digital output to the 10 bit. When the size increases, by default, this value means resolution will be increasing, decreasing. In a number of resolution will be decreases always inversely to the number of bits. That's why as this goes from 10 to 11 bit, by default this value will be 5 millivolt, will correspond to come to the near about 3 or 4 millivolt. Okay, and correspondingly this number of signals available will be increasing. So this is a basic funda that is used for conversion of the analog to digital conversion. Let's come back to this slide. Okay, so as I written here, it is not clearly visible. No issue. So this ADC has resistors. We have the ADC high resistors, then ADC low resistors, then ADC control resistors, and ADC control 1 resistors. Okay, so this ADC result high resistor, low resistor will hold the 10-bit data, 8 bit in the lower and the remaining 4 bits in 2 bits in the high resistors. Okay, so these registers in the ADC model is helpful for the conversion of this data into the input signal apply analog to the digital format. Okay. So I will save this first. So now we'll get the next slide. So after that, we have the first register that is called AD con registers. Okay, that is the 8-bit size ADC con register. How this SFR, facial function register, is helpful for the conversion of this data analog to the digital format. It is shown here. Okay, so we talk about the bit number 6 and the 7. That bits are used for a selection at what clock the conversion will takes place. Means clock required to conversion that will be decided by the these two bits. So as it having the two bits, you can see the answer. AD con registers in that ADC 0 to the ADC 1 that will decide that clock frequency for our conversion. Okay, when there is a bit will be 00 by default, F oscillator by divided by 2. This clock frequency is for the conversion. And when these bits are going from that 01, 10, 11 like that, and obviously this bit will be helpful. Conversion will be increasing, clock frequency will be decreasing. The represented by 8, a oscillator by 32, and for the bit 11, that will be what is the crystal available inside the oscillator that will be used for the conversion of the analog to the digital data. Okay, the similar way it has ADC con 1. In that we have the ADC S2 register that will decide also when there will be initially it is 0, that will be taken care of the clock frequency of 10 divided by 2 divided by 8 divided by 32 like that. But when this bit will be 1, the higher conversion will be that is available by 4, 16, 64 that can be used for the conversion. Okay, so this is for what? At what frequency of the clock signal the data will be converted into the analog to the digital format that will be decided by the these two 4 bits. Okay, then this CH1, S1 and CH, S2, S0 to the S2. These 3 bits will decide that as 3 bits are there means what? Maximum configuration, we have the 2 raised to 8. Okay, so these 3 bits CH0 to the CH1 means we have the 3 bits. So these 3 bits will decide at what input signal am I applying the. So these 3 bits will decide that at what input signal is analog signal is applied. So these 3 bits are there. 2 raised to 3 will provide me 8. So we have the 8 input channels in case of the 40 and 44 pins. So out of this 8 input channel, I can apply the analog signal as to the one of the input signal, and that will decide at what data it is going to be converted. Okay, let's see that. See here, CH0 to CH1. So from that 00 to the 111 will be there. That will provide the N0 to the N7. So these pins will be used for the taking the analog input signal. We can apply to the end of the input channel. Okay, then the bit number go done is there means what? The conversion of ADC current will be takes place. But 0 will be there, it is not in the progress. Okay, when means go or done bit is the 1 that indicates that conversion will be takes place automatically. And the last bit number 0 will be AD on. That will indicate that the supply voltage is applied, means ADC on chip is there, it would require to apply the supply voltage, and that is going to be powered. When this bit will be 1 means the supply voltage applied to the internal ADC. 0 will be means ADC is off in this case. So when this will be 0, no use of this applying the input signal analog to the ADC, means it will not convert the digital data. Simple meaning. Similar way, we have the AD con register also, that will be helpful for the conversion of the data. Okay, so after if we see that ADC S2 we have seen in the previous case only, depends upon the 0 or the 1 bit, how the clock frequency is going to be selected. Like bit number 7 is called ADFM, that will provide the what is the format for the result I am getting as a 10 bit. So ADC result format select bit is there. Okay, so this decides if the bit number 7 will be 1. We have the 6 most significant bits as address as read by the 0. Means right justified. 6 MSB significant bits. MSB bits will be as a address. Result will be stored in the address H result register. And when this bit will be 0, the 6 bit will be LSB will be held in the address low registers. So we have, as I said, that we have the 2 registers for the storing the result, add ADC result L, ADC result H, higher and the lower. So based on that, 6 bits will be stored in the either of the registers. Then we have PCF0 to the PCF1 to these 4 bits. And these 4 bits will decide that configuration word of the ADC. That is called as a AD configuration, port configuration control bits. Okay, so based on these bits, channels available AN0 to the AN7 that can be used for the multiple purpose. Okay, so the signal can be applied, it is analog or digital. Need to be, when we apply an analog signal, I need to make this, all the bits will be 000, means PCM, PCFG0 to the PCF0, all bit must be 0. Then the 8 input channels can be act as a analog signal along with reference that we did in VA supply voltage. Okay, and when of the this bit will be changing from 0 to the 01, that pin number AN3 will be act as a V reference. Signal voltage is going to be V reference on that pin. Like this, when the data will be changing, it can act as a digital input pin or the analog input pin. Okay, means this ADC pin available at one of the port, that is the either port A, B, C, D, E. So that will multifunction. So I need to use that as a digital data or the analog. So when I need to use all the pins digital data, this port configuration control bit will be 0111. So after 011, any bits that act as a digital output data. So here is shown that how it is going to be converted, the data. Okay. So I'll show it here. I will use the different color. So that port A along with the 5 pins from the port A used for the ADC input. Okay, port A, and remaining 3 pins of the register port E. So port E, 3 pins are used. So total 8 input channels are available. So these 8 input channels, either I can apply the input will be either at the one of the pins. So I can say N5. So 5-volt signal I'm applying 0 to 5 volt by varying the port. And based on that, I'm getting the digital data here. Okay. And that will decide the which channel I'm applying that based on the CS0 to CS2 bit. And that VIN signal I'm internally connected to the ADC, and the ADC output will be available in the that AD register H and L, AD register L. Okay, so that will decide based on the that ADF ADC result bit format register. If we 1 bit there where 6 bits are stored as MSB in the H register, and this ADF bit will be 0. That time the 6 bit will be stored in the ADC AD result L register. Okay, so like this ADC will be converting what is in analog signal applied here appropriate in the digital format. And how it converts, as I said that for every 5 millivolt, it will change the input data because it has the resolution of 10 bit. Okay, this is the operation of ADC. Let's go to the next point. Just to discuss these things. How to select, how to convert. The process is given here, and after conversion, how it will be cleared. It is shown here. Okay. So 10-bit result ADC, that is ADFM bit, decide that if it is 1, it go result going in the address register 6 bit in that, and the remaining 4 bit in the lower register. Okay, and the ADFM will be 0. The 6 bits will be in the ADC L registers, and remaining 4 bits in the ADC H registers. That is the format. Result will be stored in the ADC result H and L. It hold the 10-bit result. Then this is the IO port operation that is in the chapter number 6. Just it is made with the either a P-type or N-type CMOS, and the logic is given. When the N-type will be there, we need to apply the 1 here, then it will be on only. 0 will be there, it will be off. And in case of P, we require to apply the 0, then it will be on. If we apply 1, it will be off. So I will not explain here port operation. Just some programs are there. Let's say that. Get the content of port C and transport to port B. So this is the program we have to write. and it is very easy. In case of if we talk about 8051, just we need to use the instruction move, just initialize the one of the port as a input, other is output. So I'm defining here the port C is act as a input. So same logic is there. Using the sending the FF level, that port will act as a output. So trace C is will be used to set the bits of the port C. That is meaning of the port C will be sending high level data. It acts as an input port, and trace B for the making 0 bits I'm sending on that bit. So port bit act as the output. So we are defining in case of 8051 like this: move P0. If it is port 0, I'm sending the hash FF data. Okay, so that will act as a input port, and the same value I'm sending 00 hash 00, that will act as a output port. This is for the output. This is for the input. In case of 8051. Similarly, I'm configuring that. After that, I'm sending, if I want to take the data from that, just I'm sending the move, I'm taking the accumulator and then transferring the other port. Same thing I'm doing here, starting the over 00, clear trace B. Okay, so by clearing that means it will be 00, act as output port. Set F trace C, that will make it as a input port. Setting means what? The port at C level goes data high. That is going to be, as I mentioned, FF. So that becomes a input port. Now, contents from the port C, that is the input port act, I'm taking inside the work registers, and that work register sending to the port B. So move F port C comma W means what happens? The contents are at the port C will be transferred in the work registers. Okay, and this content means simply I'm doing like that. If you talk about 8051, move, actually operation will be reverse in that, A comma P0 means contents are available in the port 0 will be getting in the accumulator. Here I'm doing in the reverse way because format of instruction is going to be different. So move F port C comma W means the contents in the port C what is coming, it will transfer in the work registers. Okay, after that is no operation of instruction. After that, move WF comma port B means what is the content available in the port B will be transferred to the other port. That is our task. So port C contents transfer to the port B. So the contents from port C are taken to the work register, and that work register will transfer the data into the port B. Okay, and this go to loop. So we're writing jump up. So that will keep in the loop continuously. Similarly, if I need to transfer to the P1 port, I will use P1 comma A. So this is in the 8051 simply, and it is in the peak microcontroller. So reading from the port C and transmitted to the other port. That is the simple instruction of that. The next program is just write program to toggle the all the bits of the port B, port C, and port D. If you talk about port A, B, sorry, not A, B, C, and D, it is a 8-bit port. And similar way, if we talk about just we need to send the data FF in the 00 level, or either F555 in the A, will toggle the alternate bits of the ports, what is available here. So first thing is I want to make this port as output. So need to transfer the data on this port is going to be high level data. So first make it 00, then it will act as output port. So instruction using for that, clear trace B, clear trace C, and clear trace D. So all the ports will be available with the 00 data. Okay, so that means it acts as a output port. Once it is made output port, thing is that I need to take the data into the accumulator, means in the work register. So I'm taking the data 0F in the work register and I'm transferring that data to the port B. So what is the data available in the work register F0F will be transferred into the port B. Okay, similar way, after that I'm calling a call delay, means it is a, here is the instruction is a call simply, so call delay for some time interval. Okay, so data on the port B available, 13-bit data is going to be 0FF. So this 4 bits 00 and then all bits 11. That is the data available in the port B. Then for some time delay, call delay subroutine will be defined. Then move LW 0 F0. So it was the lower. I'm taking the masking means what? The lower bits LSB 4 bits will be high data. In case of port C, I'm taking the higher bits of the F0 data. So that data I'm transferring again into the port B. So port B I'm getting with the it's like simple toggling. 4 bits upper 4 bits will be low, then upper bit is high. Now I'm doing the B with the upper 4 bits will be high. F0 means it will be 111 000. Then a call delay again. This thing also can be changed. I can make FF00 that way also. So that will toggle the port B. Similarly, for the port C, it's 99 and the 66 I'm transferring on the port, taking in the work register and then transferring to the port C. That will toggle. The last port, as I said, that AA, I'm taking the work register similarly and transferring the data on the port D. So port delay starts blinking. How much time? A call delay. And then after the delay, again I'm taking the 55 in the work register and that will transfer to the port D. Okay, and go to up means up is here. So this will keep in the loop continuously. So means port C and D will be port B, C, D is going to be making on off for different time delay. The next program is simple write arithmetic program to toggle the bits of the port B with 55 and the A. Just previously seen like it is same code is there. If you want to compare this with the 8051, the instruction used what I'll write here simply same code was there org 00. Then I need to clear B means what? I'm sending move. We talk about port 0 comma hash 00H. Okay, after that I need to take the data into the I can take directly in case of port 0, but here we need to take in the accumulator first and then I'm transferring. So I'll write in terms of the accumulator only. A comma hash 55H. Then move just P0 comma A. And then call delay, that is a call delay. Okay, so the bits 55 means what? The port will toggle like this 01 01 01 and 01 means the bits number odd bits will be high and low even bits will be low. Now next time I need to do the reverse operation. So I'm sending the data in the A with the AA move A comma hash 0 AA H, and this data goes to the move P0 comma A. So that time these bits will become 10 10 10 10 means it is A. Means now even bits will be low and odd bits will be low and the even bits will be high. Again calling the delay. So A call delay. And if you want to keep in the loop, I need to use the S jump up. So up I'm writing here. Now similarly in the P control, what I'm doing, OR the 00. So configure the address from the 00 and then make the port B I'm toggling. That's why I clear the port B. That will make it as a output port by clearing the port. Then take the data in the work registers, that is move LW. Here in this case, the syntax is totally different. Don't we need the comma, all these things. So move LW, direct data 0x55u. And 0x writing means it is by default X value. So the 55 will be getting the W register, work registers. And that I'm sending to the port B. So in the case of port B, the data is coming what? 0, 1, 0, 1, 0, 1, 0, 1. Okay, then I'm calling the delay. Same thing like move A comma FF, then sending move P0 comma A. So contents of A will come in the P, here reverse way. So content for register code in the P, the data. How much time? Define call delay. So here is case A call delay is a syntax, but here is a simple call delay. After that, I'm taking in the data in the work register AA. Same case, move A comma AA, hash AA. So this data I am sending into the port B. So port will be now 101010. So in case of that, low odd bits will be low and higher bits will be even bit will be high level. Again, a call delay. And like edge jump, I need to use the go to up. So this will keep in the loop. Okay, so this is a simple comparison of the port toggling in 8051 and the peak controller. So I will clear this drawing all and go to the next. Similar way, if you connect the pin to one of the port pin, and I want to make that LED is on off. So here is the code written for that. So an LED is connected to the port D. So at port D, I'm connecting LFT, right? Assembly language program to make the LED on from pin number D7 to D0 to D7 means 8 LEDs are connected to the port D. As the port D's size is going to be 8 bit, so 8 LEDs are connected, and that 8 LEDs I want to make on off on off. Okay, so for that code is there. Same thing as I discussed toggling, we need to send a FF and the low loaded data. So or the 00 will start the address, then the port D act as output. So clear F means the port D will be act as output port. Then BSF means the port 0. BSF is a bit set. The port D means the port D is going to be set at the high level. So contents of the port D will be 1 means it is high. So LED is connected is going to be on here in this case. How much time will be on? Call delay. So delay is calling. Up to that delay, it will be on at the port D. Okay. After that, it is 0,1. BSF port D. Again, bit set F port D. So the port D becomes now high. No. So it's a 0 pin is going to be on. Next time I'm doing the port 1 pin will be high. And like this port D, go on continuation. So I can make the high level pins on the connected here. So this port D indicated 0 means the bit D0 will be on, then D1, D2, like that I can continue for the D7. Otherwise, I can send the data, I can take the data into the work register FF, and I can make all the pins on and hide them same. So I'll write the code different here. If you want to make all the LEDs on, same way, ORZ00 H, then clear CLRF trace B trace D. So that will make the output. Then rather than using that BSF, I'll use move F, move LW. In the work register I'm taking directly 0x FF value. Okay, and then I'm transferring to the port D. So move W, comma port D. Then call delay. So this will make the port high, D port. How much time? A call delay. After that, take the 00 data into the work register and send to the port 1. So what will be there? After that, next continuation here, move LW 0x0, 0. This data I'm taking. Again, then move WF port D. I'm sending that 00 to port D. How much time? Call delay. So sending the 00 data, it will make the LEDs off. Okay, and this will be in the loop. Go to up, and lastly end. Up I need here. So every time I'm sending FF on the port D, it will make the LEDs on for some time delay, then send the data 00, that will make the LEDs off at the connected to the port D. So this is alternative way, what is the code written here, to make the LEDs on off in case of the peak microcontroller at the port D. So here is the code to generate a 50% duty cycle on the port C. So thing is same, set the port high, call delay, then set the port 0, and then call delay. That will generate the 50% duty cycle. Well, like you are doing, set B, P0.0, and clear P0.0. At particular pin, I'm generating the square wave. So at the ports is mentioned. So first I'm starting with that at 00, and I'm clearing bit clear file is 0. Means what? The port C 0 bit is going to be making clear. Okay. After that means this port acts as a output port. That pin particular 0.C pin act as a output port. Then to make it as high, I'm using BSF, bit set file port C, comma 0. Means port C 0 number pin I'm setting to the high level. Once it will be high, call delay. Okay, after call delay, I need to I need to clear that. That's why bit clear port C, comma 0. That will clear the file. Means if we talk about this is my P controller, and at the port C, pin number 0, I'm first making it as the output pin, and first I'm sending the high level data. So it will the signal goes high level. Okay, how much time? A call delay. Bit set file, it will make high. Same like a set B in 8051. After that, making on for some time delay. After that port pin, I'm going to set to the low by instruction bit set bit clear. So BCF indicates bit clear file port C. So this will be clear for the that time delay, a call delay. The delay will be same. That's why I'm getting the on off cycle in case of the at the port pin 0.0. So that will be the 50% duty cycle. Now, simply in that same code, I will change. I want to make it a 60% cycle. What is the logic to be changed here? Just we need to apply call delay 2 times here. So after this also, I need to use one more call delay that will produce the 67% duty cycle. How? Same thing is there. You can see after setting the bit set file port 0. So this port I am setting for the 2 times time delay. This will be high for the 60%. After that, making off for some time, short time interval. So this delay is going to be half as compared to the this delay. So the bit C pin will be high for the twice the time delay. That's why it can produce the 67% duty cycle in case of when I'm calling a call delay twice. And then I'm clearing that. This logic is there, so code will be changing as logic is changing. So you need to understand what logic need to be applied, and I can write the code for that. Okay. I think you understood this code simply, rather than taking the too many codes. All the codes written here. We'll stop it here. And next lecture, chapter number 7 also is finished. And from next lecture, we'll start with the chapter number 8, that is serial communication. Okay.